Welcome to the February 21st, 2025 episode of The Energy Show. I'm energy journalist Markham Hislop, and my guest today is Tyler Norris, who is the lead author of a study that I think you're going to find very interesting. And he is a PhD student at the Duke University in North Carolina. So, welcome to the show, Tyler.
Thanks so much for having me. It's great to be here.
This is very interesting, and regular viewers and we've been around. This is our 17th year, so we've been doing this for a while. And our the media, energy media gang knows that our fundamental premise is that it's an electric future. That's where we're headed, and that any country, any economy that has a grid that's low cost, clean, and reliable, that's gives it a fundamental competitive advantage. And so everybody's electrifying their economy. Certainly the US is, China, Europe, parts of Southeast Asia. And it's not just about adding new supply or transmission, it's how clever can you be? And that's what struck me about your study, which is titled, give me just a moment, Rethinking Load Growth. And you're with the Nicholas Institute for Energy, Environment, and Sustainability. So give us just a brief overview of the argument in your report, please.
Yeah, sure thing. And I think you said it well. As background, this study was inspired by conversations with utility regulators, primarily in the US Southeast, during 2024, because they're all grappling with huge amounts of load growth in their jurisdictions. And there was this very interesting juxtaposition that was revealed in those conversations where, on one hand, the regulator said, we're informed that these new loads are 100% inflexible. They may be at 100% load factors, operating nearly all the time and not capable of any sort of ramp up or ramp down. Um, and at the same time, though, we were seeing, the Secretary of Energy's advisory board and the Electrical Power Research Institute had just come out and put a big spotlight on this concept of load flexibility as a way of enabling load growth in a faster and more sustainable way. And there were other kind of data points. We saw one big utility out west, PG&E, launched this Flex Connect program kind of in that space. And so the idea was, and the clear message we got from regulators is it would be helpful to get more analysis and characterization of what's actually going on here and what are the possibilities. And so we started digging into it. And I'll tell you, we weren't well, actually, at first, we were just going to do a sort of qualitative characterization of what's going on in this space or what the capabilities may be. But we thought, let's run some numbers just to see what it looks like. And, we thought there'd be something there, but that, you'd have to curtail a pretty substantial amount. So it'd probably be, a little bit of curtailment and then some capacity addition. But honestly, the numbers were so impressive on the amount of headroom, available capacity on the existing power system that we ended up running five different scenarios actually for load curtailment rates. And I have to say we were quite surprised by the findings and even arguably with pretty conservative assumptions. So, I mean, in a nutshell, the findings are that because our electric power systems are underutilized most of the time because we build the systems to these few hours of the most extreme peaks during extreme weather systems, we have underutilized capacity most of the time. And we can add a lot of load to the existing system if they're able and willing to be flexible for a few hours of the year. Now, and then we quantify exactly how much we're talking about, but a relatively small share. And what we're really talking about is, 0.25%, 0.5% of their maximum uptime they would need to be flexible to enable all these load additions.
Hey, I've had a number of experts on my podcast, Energy Talks, and as well as on the show. And the comments from Gerhard Schlager, who's Hitachi Energy's chief technology officer, really stuck with me. He's a grid engineer, and he said the grid of the future is not going to look like the grid of today. It's going to be far more flexible, implementing all sorts of technologies that will enable us to get more out of the grid we have, like reconductoring, where you take old lines, you replace them with high capacity new lines. And he said, we're getting really smart about how we can take our grid and make it so much better without just adding stuff, adding new power generation, adding new transmission, new distribution, all of that kind of thing. And what struck me about your study is how little, and you just mentioned it, how little we have to do in order to make this to provide that headroom that you're talking about. Now, you're mainly concentrating on industrial and commercial supply, if I understand. That's what this is about. This is not about residential consumers. So, what kind of industries, let's say, can curtail their electricity demand when they need to?
Yeah, and thanks for mentioning that. Let me offer one point of clarification, which is that, I mean, theoretically, this load flexibility could come from any type of load as long as it's
Sure.
able and willing to offer flexibility. So it could come from residential, it could come from other types of commercial, but because most the largest driver of load growth, at least in the U.S. right now, is large commercial and industrial loads. We wanted to focus there because it's easier in some ways to have a conversation about how do you treat something that's new rather than how do you change, the treatment of the existing loads. You can do that too, but and the other advantage in this case is, we're talking about such large scale loads that you get the benefit of kind of centralization in a sense where, if you're able to implement that capability on one load, you can get a lot of, whereas if it's across the smaller, more distributed loads, right, you have to sign up thousands of customers, right, to get to that kind of
Yeah.
scale. So, I mean, in this case, we really wanted to focus on computational loads, which is just a fancy term for data centers, and crypto mining, but especially the data centers, because that's really what's been one of the biggest drivers of the increase in the U.S. load forecast over the past 18 months. And it's completely overwhelming some of the jurisdictions here. I mean, just to give you an example, AEP, it's a utility in Ohio, they had already signed up 5 gigawatts of new data centers and then ended up with requests for 30 gigawatts of more data centers coming on, which, would be like multiples of their existing peak load. So they actually had to implement an entire moratorium on new data centers, and then they've been reaching a settlement around that. But one of the reasons why there's a lot of interest right now in the data, one, because there's such a big driver of the load growth, but two, because of the change in the computational profile, the profile of their computational loads. And critically here, what's interesting are the training loads, right? Where you're training the neural nets or the large language models. And what's different about training workloads is that they're much more deferrable, or you might say schedulable, than traditional computational loads, which are more, real-time, on-demand cloud services where you can't schedule them, right? Because it's just in response to the customer in real time. But when such a substantial portion of your load is for training, this is very different. And so because of that and several other factors we can talk about, there was this interest in trying to figure out what's the there for the data center loads.
Oh, that's very interesting because data center load was a big issue a few months ago and late in 2024. And then DeepSeek came along, the Chinese model, which is much lower cost and it looks like it has its energy requirements are much lower. Does that change your computation and your calculations much?
We didn't plan the timing, obviously, because we didn't know that DeepSeek was about to be released, but
Sure.
it ended up, I mean, in an interesting way, really, I think, reinforcing the value of this kind of approach because what it has done, of course, is introduce significant uncertainty into what the ultimate data center load forecast is going to look like. And as a regulator, that's concerning, right? Because if you're going to be approving large expenditures on new generation and new transmission and new distribution capacity to accommodate, a data center load forecast, and then it doesn't show up, well, then your general ratepayers might be on the hook for that. And the way we characterize it in the report too is that load flexibility and planning for some degree of load flexibility offers sort of a hedge against the uncertainty introduced by DeepSeek. And so we can still, be adding these loads. Of course, we'll still be investing in some degree of capacity expansion, but it buys us time, so to speak, so that we can see how this plays out and ultimately to see as well, like how flexible can these loads be? Because all of this is sort of evolving in real time. The capabilities are improving in real time. And so we're all kind of trying to figure out like what can be done.
This idea of flexibility and risk management is a really key one, I think, at a time of uncertainty. And just on a related issue that Energy Media is involved in, Canada is trying to figure out how to respond to President Donald Trump's threat of tariffs. And one of the response on the oil and gas side is, well, let's go build pipelines. Well, why would you take 5 to 10 years to build a linear infrastructure that is designed to last for 50 years in response to an immediate threat that might see your customer demand change within a month or two? That's not a smart response and it's kind of the same principle here. Lots of uncertainty, lots of change in demand, don't know where it's coming from. Your assumptions might change in a very short period of time, like yours might with DeepSeek. And so managing flexibility in there so you're not trapped with investments that then become uneconomic down the road or aren't as effective as they could be. That just makes a whole lot of sense to me.
That's right. And, the term of art, of course, would be, stranded asset risk, right? The risk that you end up putting a lot of investment into an asset that doesn't become fully used and useful over its life, which is the term of art too that's used in the utility regulation space. And so, that's exactly the eye that regulators should be taking to these decisions. But one thing I do want to emphasize, which you were getting at, is that even though our report was a little bit more oriented toward data centers, this flexibility, it could be from other industrial customers too. And I think, the clearest example of that would be to the extent that the industrial customers may have their own on-site backup power or battery storage that they can tap. And of course, the cost of the battery storage has come way down. And what we quantify too in the report is that, the duration of curtailment that's necessary to unlock a lot of this headroom, it's on average about 2 hours, which looks very close, right, to the profile of a short duration lithium ion battery. And of course, in some cases, it's an average. So in some cases, it's a little longer than that. But, even a 2 hour or a 4 hour lithium ion battery could go a long way, including for an industrial, factory or otherwise.
Yeah,
And I will say, this is important to note too, is that, so one company, that we highlighted in the report and was very excited about the report, they're called Enchanted Rock. And, they are developing on-site natural gas power plants for data centers. And, I'm not opining on, whether that's optimal or not. It's just a reality. They are doing that.
right.
And they're for the system, I mean, because the thing is, the data centers and a lot of these industrial customers, they have to have fully redundant backup power already, right? So you're already developing redundant capacity. It's just that to date, most of that redundant capacity, the backup power, has been these tier 2 diesel generators, which they do create a lot of local pollutants, and so there are environmental restrictions on how often they can operate, and actually whether they can operate at all. But natural gas is an improvement over the tier 2 generators, though. So, it depends on what you're comparing it against. But I want to emphasize that too, because, this isn't necessarily going to favor one particular technology or another. It can, right, if you make the intentional effort to ensure that it is. But I just want to make sure that's clear too.
Yeah, and there's lots of ways to skin this cat, as the saying goes. Because I was talking to I interviewed a couple of years ago a business person in San Diego, and there they have very high power prices. So there's a lot of interest in business and industry in industrial parks and commercial parks in putting in microgrids where this operator will have solar or wind or whatever it is, and a battery system, and then link all of the businesses. So you can imagine a scenario wherein, because very often industry is in clusters, right? I mean, they're not one here and one there. They're all together in a park. And so you have a microgrid and they share a battery capacity. So it's not necessarily that the refinery or the factory or whatever it is has to invest in its own expensive infrastructure, like a battery setup. It can share it with other industries. And so there are lots of ways to imagine this that's very cost effective for the customers.
Yeah, that's a really interesting point. And one thing I think it also relates to is that you might end up seeing a mix of different backup generators, battery storage, and flexibility capabilities that sort of work as an orchestra, right, to provide this flexibility. So it doesn't have to be one or the other. And another sort of key finding from the report is that we just talked about the duration of the curtailment events, but it's also important to consider the magnitude of the curtailment. So how much of the new load would have to be curtailed during these events? And based on the modeling we did, in 90% of the hours when there's any amount of curtailment, at least 50% of the new load is retained. And I have the numbers are there in the report. But the bottom line is during most hours when some curtailment event occurs, most of that load is retained. And so what that means is that you might be able to, you could size the battery such that it's only, say, 20 to 25% of the max draw of that load. And you could get a lot of flexibility out of it. You don't have to have, the battery size at 100% of the new load. And it could be in concert with other, right? So you could have the battery, for that 25%, and then you might have some natural gas as an additional backup that could provide flexibility. And then maybe for the rest, you have, the tier two diesel generators that you don't want to run very often. They're there in the worst case scenarios. So you can see how, a variety of resources in the type of setting that you described too could contribute.
Now, one of the economies in Canada that comes to mind immediately is Alberta, which is kind of our Texas, right? I mean, it's the Alberta all by itself is the eighth largest oil producer in the world. And when you combine it with the rest of Canadian production, that's Canada is the fourth largest oil producer in the world. Bigger than Iran and Iraq and a lot of other countries that get far more attention. And so there's a lot of, as you can imagine, there's not only the production capacity, but also their refineries and upgraders and petrochemical plants. Again, the second largest petrochemical cluster in North America, behind Texas and Louisiana. So some of that load can be flexible. But if you've got a petrochemical plant where you have material that's moving through your plant, maybe not so much. So there would have to be planning involved in this, so that those plants, those operations that are capable of more flexibility, plan in a different way than those plants that are not. And what this suggests, and I bring this up because the U.S. is very different. You have the regional transmission organizations, are the RTOs, and you have regional regulators. You have FERC. We have none of that in Canada. It's all provincial. We have Alberta's different because it has a wholesale market and a system operator, but all the other provinces have like crown corporations, like a government-owned utility monopoly. But that in a way makes it easier because now you maybe have a regulator, you have one utility, you don't have 15 utilities, and you can do this kind of work The issue is getting it into the corporate culture. The kind of work you do a study. The grid planners in BC Hydro, where I live, read that and go, hey, we have pulp mills, we have sawmills, we have loads that can be variable. We never thought of that. And how do we get this into the planning process?
That's exactly the right question, I think. I'll just note that, so 40% of US electric load is under non-ISO RTOs, right? So it's a similar arrangement where the state public utility commission so it regulates it's a regulated monopoly, right? Investor-owned utility generally. I think the advantage that Canada has, if you have fewer provinces than we have states, because what we end up with is this highly balkanized system where every state's a little different. That's not in an ISO RTO. But to your point about planning, this is really key. So we've been asked, how is this different from all these existing demand response programs that are out there, and which have made meaningful contributions? And just as a metric, like in MISO, the Midwest Independent System Operator, which big electricity market in the U.S., 10% of its peak load is serviced by demand response, and 70% or more of the customers that participate in that demand response are large commercial and industrial customers. But for those loads, they were all planned as fully firm loads. So when the utility or the system operator looked at those new loads coming in, they planned the system such that they would be 100% inflexible, right? So
Oh,
that
okay.
means that that their plan, that they contribute to the full reserve margin, right? You have to have the backup sort of supply, and then of course you're planning the transmission expansion based on that new load. Later on, they might have decided, well, we want to participate in this demand response program that's being offered because of the economic incentives involved to put, some say downward pressure on those peaks. But what's different between that and what we're talking about is the planning piece, because what we're talking about is pulling all this up on the front end. And when you're thinking of, planning your generation capacity expansion and your transmission, acknowledging that potential flexibility and incorporating it into your resource plan. And, to your point, when you do have, these kind of regulated monopolies, you can have this more integrated planning paradigm. And that's what we've been trying to get better at. We've had what we call integrated resource planning in the US for, in different jurisdictions for a few decades. But it was only recently that everyone realized, well, we really need to have like an integrated transmission planning process too, that's also incorporated into the generation planning. And now we're saying is, look, because of all this load growth, like we also need a load planning. The load plan has to be, like deeply integrated into that on the front end.
Yeah, this is really interesting because BC Hydro just released its latest integrated resource plan, and it's calling now after 15 to 20 years of flat growth, no growth. Now it's calling for 2% a year, and we might even see more than that. I suspect. I think that's a conservative amount, and so they're looking at all sorts of different ways to do this. That's clever and doesn't, we have 30 or 32 hydro dams here. We're almost all entirely hydroelectric power. How do you expand generation, for example, without building more hydro dams? Because they can't, they've run out of capacity. Well, one of the ways is you can have independent power producers build wind and solar farms. And then you can contract for that power, and it works very nicely with the hydro dams. The hydro dams acting as kind of like that's a clever approach to this. And then as they add, because they're looking at hydrogen, they're looking at LNG plants, they're looking at probably at data centers, I would imagine. They could take this idea and say, for that new load, now we're going to build in flexibility so that in the middle, when BC has a cold snap and electric demand goes up, we've got that covered. In the summer, when it gets hot and air conditioners kick in, we can manage that without a lot of new transmission planning and transmission construction and the expense that goes with it. That's really kind of what we're talking about, isn't it? And planning for the grid you've got, as opposed to some kind of grid that you wish you had.
Yeah, I think that's exactly right. And look, the systems are already built to accommodate really extreme swings in demand. I mean, that's the reason why we have these reserve margins. And in some cases, oftentimes the average people say is like 15%. But I mean, we have major jurisdictions in the US that have, in excess of 20 to 25% reserve margin on top of the peak that they forecast. Right? We've already, I mean, in a sense, right, we've already overbuilt the systems. And part of it is that, I mean, for justifiable reasons, right, when you didn't have all these very sophisticated, control systems where you could sort of precision, uh, flex a certain load or, redirect power in various ways. And that kind of, when you have limited tools from an engineering perspective to modulate, you want to err on the side of being extra conservative, like in every regard, right? And that made sense in a certain environment. But the environment we're in now is one where we're just increasingly resource constrained, and our supply chains are constrained, right? We have so many demands now on the power system, right? Because as you said from the beginning, it is kind of the mantra is electrify everything. Well, there's only so fast we can move. And like we can only hike up rates so much, right? Before there's just going to be a backlash or a saturation point. So the more tools that we have in the toolbox, right, to just get like more utilization out of whatever system either we already have or that we're building to. I mean, the point here is definitely not that we shouldn't be investing in expansion of generation or
Right.
transmission. We need to do that for a whole bunch of different reasons. But there are just constraints on how quickly we can build that out. And so this tool, in a sense, I kind of think about it as it buys us time so that we can focus our limited resources on the highest value upgrades to the system. That's where the planning comes in, right? Because you really need to do the detailed cost benefit analysis to identify which upgrades are most important. And then it buys us time to focus on those.
I sit on the media panel for the U.S. Energy Association when they do these monthly technical briefings. Not everyone, but I've been on enough of them now, and very often we have utility executives in, and they might be RTO executives or system operators like CAISO, that kind of thing. And you should see the worry and concern on their faces when they talk about these very issues, because they need to add supply, for example. Where are you going to get it? Can you get solar panels? Can you connect a solar farm to the transmission line? Can you get, how interconnection queues are huge and they're not moving very quickly. I mean, they are really worried. Oh, and then there's the whole issue of retiring coal and gas faster than the US can add additional supply from other sources. This is a really serious problem, and NERC, the North American Energy Electricity Reliability Corporation, which also includes Canada, is warning all the time about system unreliability, potential outages in extreme weather, that sort of thing. So I don't think we can overstate how important it is to bring these new tools to the table, because this is not a crisis. Well, what's just below a crisis? It's a serious issue.
Yeah, it certainly is. A couple comments on that. So, we cite, of course, NERC's, 2024 long-term reliability outlook, uh, and it's an excellent report. They do it every year. It's a remarkable resource. One of the big headlines that came out in December, right after NERC released that report, I think it was in Utility Dive. It said, new. I'm paraphrasing here. It says, new report suggests that half of U.S. load could be at risk of blackouts due to load growth. And we have to be careful of this crisis mentality too, though, and because that's a very interesting headline. Because the thing is, there's nothing about adding new load that should necessarily increase the risk of blackouts to existing load. The only reason that would occur is if you make an intentional decision to treat the new load on the same playing field as the existing load. And you can make that decision, but let's be very clear. I mean, and what it gets at too is I mean, if I'm a regulator, right, I want to know what is the curtailment priority in the case where we have to have load shedding. And of course, you'd say, well, it's going to be, hospitals are retained, they're prioritizing critical infrastructure. Where do the computational loads, sit in this prioritization? It does get tricky, but yeah, we are in, a very resource constrained, supply chain constrained environment. We've got to be looking for all the tools that we can in the toolbox. And well, we could have a whole conversation about the generator interconnection queues. That's actually one of our kind of research focuses as well. But there's a lot we can do there to speed up the process too. And I think ERCOT's done a great job with kind of figuring out more flexible ways of adding both generation and load. And they've been a leader in kind of thinking about these more flexible kind of service options.
Yeah, and I've done a number of interviews with experts about the Chinese power grid, for example, where they're adding huge amounts of renewable to intermittent generation and all the problems that that causes for managing the grid. So it's not like this is just US and Canada. This is a international phenomenon. Wherever you've got a grid, it's probably experiencing rapid growth of, the 2, 3, 4% a year, about who knows, maybe more. And everybody's grappling with this issue of how to maintain reliability and keep costs down while you grow the grid and decarbonize it at the same time. I mean, the challenges here are not insignificant.
That's right. And it's important to, I think, underscore that part of the problem in the interconnection queues and why there's such a large backlog is because you we have these resource adequacy constructs, which can also be referred to as capacity markets. And we've made an intentional decision to structure our electric power markets such that new generation and load, but even starting with the generation side, you're studying the new generators so that it's called what we call fully deliverable. And what this means is that it's considered a capacity resource. And what that means is it's subject to much, much more rigorous criterion in these interconnection studies, which one, right, it assumes that it's discharging at 100% of its max rated capacity. Two, that it's subject to a bunch of contingencies. And then three, there are all these local cases they look at. That adds up to is it's much more likely to trigger the need for more transmission capacity. And ERCOT has taken the completely opposite approach, right? They don't have a capacity market or a sort of resource adequacy contract. Everything is treated as energy only. And as a result, they don't have to study the generators for what I just described, like this really rigorous deliverability criterion. And so you can just connect to the grid and ERCOT will tell you when you can operate, right, based on their reliability constraints. But it's a little bit more of a come one, come all. The system operator will figure out, that a new generator needs to be curtailed to preserve reliability and stability of the system. But when you have this kind of flexible construct, it allows for generator additions at a much faster pace, and their pace of interconnection is much more quick. And you can imagine a kind of similar paradigm on the load side.
So if I could summarize what ERCOT is doing, Tyler, and actually ERCOT looks a lot more like Alberta than any other kind of market design. So this is pertinent for Albertans. But it's basically ERCOT says, come and connect. We'll figure out how to manage it once you're connected. Whereas everybody else says, hang on a second, we're going to do a study to figure it out ahead of time. It takes 2 or 3 years, and then you have this big queue of projects waiting to connect to the grid, and that causes all sorts of problems. And now I think ERCOT's approach is getting a lot more attention, and people are starting to think, oh, maybe that might work for us. We should give that a try. Is that a fair way of describing it?
I think so. Yeah, I mean, it's worth noting. They do a study, and they give the results of that study to the interconnection customer or the generator that's seeking interconnect, and then the generator can understand what is its likely curtailment rate going to be based on the results of that study, and then the generator can make an informed investment decision, right? Whether it can accommodate that level of risk. So it's not like people are just flying blind, right? Like just plugging things in, and there's no consent. There is a study. You look at the results. You make an informed decision about whether you want to proceed. But what's enabled this is just like we've just gotten a lot better at real time operation, time contingency management. And it used to be, right? I mean, it was just humans, right? Like just running, the operating room. And,
Yeah.
you had a limited set of large central station generators, and they knew exactly the operational specs of each generator, right? And now we have a lot more resources, right, that are being orchestrated. But fortunately, we have much, much more advanced, like computational systems, right, that allow us to do that. And so the advantage of that is able to do things much more efficiently and make better use of the resources that we have.
This is funny because during the 70s, when I was growing up in northern Manitoba, my dad worked for one of the big hydro dams, the first one on the Nelson River. And we would go into the control room, and it looked like the bridge of the USS Enterprise. That's exactly what it is. There's a bunch of guys sitting at pushing buttons and doing calculations and doing. And the modern way of doing that is so much more sophisticated. And now we're looking at bringing in things like artificial intelligence to even make it more efficient. So flexible intelligence, smart grids, I mean, that's the direction we're heading. And so I think sounds like your study has made an important contribution to that. And Tyler, you've done a great job of explaining it. Thank you very much for coming on the Energy Show.
Thanks so much for hosting. Really appreciate it.